Hello, everyone, and thank you for joining. Uh, this webinar will wait a couple of minutes for all the attendees to join, and then we'll kick it off. Just wanted to mention that we'll have some more webinars coming up. We'll talk about layout editor. If you don't know layout editor, well, it's a new feature we launched this year where we change the game and how RatedPower works, and we can manually adjust our layout. That if you don't know, RatedPower is a parametric software, and now we'll be able to manually adjust the structures, the power stations, the roads, and generate those designs and get all those documents. So if you're interested, make sure to join the layout editor webinar. We'll wait a bit just for people to join, and then we'll start. I just wanted to mention also, and I'll mention it further into the presentation, that you can drop your questions, and once we finish the presentation, I'll get to them, and yeah, feel free to ask whatever comes to mind. Perfect. So I think we can start. Thank you everyone for joining this webinar, where we'll talk about the AC versus DC BESS with our arbitrage feature in RatedPower. So this is me, Cecilia Hernandez. I'm a technical advisor. I work for the customer success team in RatedPower, part of Emberus. I have a background in EPC construction for PV and BESS. I've been in the industry for about 3 years and a half, and I'll be your speaker today. Just a quick index on what we'll be talking about today. We'll do a quick introduction on BESS. I guess everybody knows a bit on BESS, but just for those that do not know, we'll do a quick introduction. We'll talk about AC and DC BESS and see what the differences are and how we connect them and collocate them with our PV plan. Then we'll see what we are capable of doing in RatedPower with BESS, and then we'll jump into doing some scenarios for AC and DC in RatedPower, and then we'll do some conclusions on what we've find out. Perfect. So let's go to our introduction. So what is a BESS? BESS stands for Battery Energy Storage System, and it's a technology that stores electrical energy in batteries so we can later use that energy. We can either do a standalone project where we connect it to the grid, or we can integrate it with any other energy source like solar and wind. So why does BESS exist, right? So we have a installed capacity of renewables that is increasingly rapidly, because we need to meet some climate targets, right, and support the energy transition. So since solar and wind are weather dependent and cannot be controlled by us, we have a major fluctuations in power generation. And this creates an imbalance between the generation and the consumption, threatening the grid stability and can lead to overloads or energy waste. Let me get my laser point. As you see here, we have a graph of the energy generation by different sources, and then on yellow we see the actual demand, which has some difference in the generation. That's why whether BESS would come into play. So BESS are essential to store that excess energy we were talking about and supply it when needed. It offers a great flexibility, balancing fluctuations and making the energy supply less weather dependent. So we can take the matter into our hands and decide when when to use that energy and not depend on the weather. So what type of BESS do we have? First of all, we have AC coupled BESS, and this structure can also be used for standalone BESS. So the storage system is connected to the grid or the PV plant by an inverter on the AC side, and this is usually located outside the PV array area. As you see here, this co-located AC coupled BESS is outside the array, and we have the batteries with the inverters. So this BESS system, we can either charge it by the PV plant we have or the grid. And we can use this for arbitrage, taking into account the prices of the energy, some grid services for frequency regulation, load shifting, peak shaving, and also curtail management if we had a curtailment at the delivery point. So basically what we'll have is PV panels producing DC current that will transfer into an inverter that can either go to the grid or to power any utility into the MB grid of our plant, and then we'll go back to uninverted, go back to DC and into the batteries, and vice versa. We can go into the grid. Perfect. And as for DC coupled BESS, this system is connected to the PV field, and we store the energy through a DC to DC converter. And we usually locate the batteries near our power station. So we can charge it from the PV plant. We can also charge it from the grid, but we may need to make sure that we're using bidirectional inverters, because when we're installing the inverters in our PV plant, normally those inverters are not bidirectional, as contrary to the AC. So if we want to do it in reverse, we need to make sure we're installing bidirectional. What can we do with DC coupled BESS? Well, we can use it for PV oversizing. If we do a higher DC to AC ratio, then we'll have more clipping. The inverter will not be able to convert all the energy we're generating, and then we can use that energy to charge the batteries. And we can also do arbitrage, charging the batteries when the prices are lower and discharging when they're higher. So we'll have the PV field going into a DC to DC converter. As you see here, we're not changing the current. We'll charge the batteries, and then when we need to discharge them, we'll do we'll go with the inverter from the PV plant and then into the grid or to power anything. Okay, so just a quick summary of AC against DC. So AC is connected to the AC side with a separate inverter, where DC is connected on the DC side of the PV production. And I'm talking about PV because we're focused on PV, but this could be the same with any other energy source, and we place it before the inverter. For AC, we need to go from DC into the AC for the PV, and then back to DC to charge the battery, and back to AC to then inject to the grid. And for DC, we'll go from DC directly from the PV to the battery, from the through the DC to DC converter, and then we'll go into AC and to the grid. So as per installation flexibility, AC, we can add an AC coupled BESS system to an existing PV, and normally it's placed outside the PV array. And for DC coupled BESS, we place it near the inverter, and we normally need to implement it in new projects where we have not already located and built the plant. For equipment cost, AC has a higher cost because it needs another inverter besides the one we're using for PV, whereas DC, we're already using the PV inverter. Curtailment and clipping management, AC BESS would be better for recovering the curtailment at the point of interconnection, and DC better for the clipping on the inverters. And for operation and maintenance, since AC is more modular, an inverter failure does not affect the system. It would only affect that BESS block. And for DC, since it's more centralized, an inverter failure can, well, stop the production in the PV block and also the BESS. So it's more or less when we're talking about string inverter versus central inverter. Well, if we have a string inverter failing, it's not as big of an impact as we have a central inverter failing. Perfect. So now we'll jump on what we can do with BESS in rated power. So rated power enables the users to design BESS, and we can choose between a hybrid plan, and this includes DC coupled BESS and AC coupled BESS, and we can also do standalone projects. How? We have a sizing tool where we'll define our input parameters, and then we also have the modeling tool. I'll quickly explain a bit on this. For our sizing tool, we'll define the main electrical and sizing of the BESS. We'll define a battery area if we're talking about AC, and DC BESS will be installed inside the PV array, so there's no need to define a different area. We'll define our power conversion systems, or the power of the DC to DC converter, our battery containers, what's the capacity requirement, how much BESS do we want to install, how long is the cycle we want to reach, and the dimensions of the equipment we're using. Sorry, we'll jump into this into the software, but just a quick overlook on we can choose between AC or DC, our PCS, the requirements. You want to set a specific capacity, but yeah, we'll see that in the software. And then, as per our modeling tool, what we'll do is we'll run a techno-economic analysis based on what we define. If now we're doing a arbitrage strategy in rated power is our newest release, and we can do arbitrage on DC and AC side. So we'll define the round trip efficiency of our batteries, the charge and discharge efficiency, how many cycles per day we want to reach, will state the maximum state of charge, minimum state of charge, and we'll set the degradation of our battery and the end of life state of health. And then on the other hand, on the financial part, we'll set some energy prices. These energy prices can either be fixed, or we can go into the market and do some variable prices. Okay, so now we'll jump into the use case I've done in rated power to compare a bit on some BESS projects on AC and DC. And I want to first mention that is BESS profitable? Well, it depends. It depends on different factors that influence our profitability. Like every project, it's not the same. Depending on where we do it, we have to take into account the energy market prices, if we're going with a fixed price, a PPA, the capex of that project, also the OPEX, the cycles per day we're doing. Is best to do more cycles per day or less cycles per day? Well, it depends. It depends if it's gonna increase the profitability or it's gonna decrease it, depending on the cycles per day. So this is something we need to study and analyze, and for that we'll use rated power. So what I've done here, and I'll introduce this scenario, and then we'll jump into rated power. So I wanted to compare the same project, but what if I install AC coupled BESS, or what if I install DC coupled BESS? So what I did is I created a 11.07 megawatts DC of peak power. You see it's the same here for AC coupled BESS and DC coupled BESS. And my scenario here is that I have a curtailment at the delivery point of 6 megawatts AC. So in this case, I'm producing 9 megawatts AC, so I'll have an excess of power on the AC side, and for that I'll install a AC battery system. And on the other hand, I brought up the DC to AC ratio to 1.8, and so I can deliver 6 megawatts AC, but also have a lot of clipping of energy, so then I can install my battery energy system of DC. So we'll jump now into rated power, and we'll take a look at these two scenarios, and then we'll do some iterations, changing some variables as we were mentioning, and see how that affects the profitability of our project. And feel free to ask any questions once we finish the presentation. I'll tackle those, and we can see if we can do any more iterations with RatedPower. So for those who don't know our software, we're a cloud-based software collaborative tool. We'll have our username and a password, and we can collaborate on different projects. So here I have my most recent projects. You see, these are some games we did for Intersolar last week for our happy hour. I don't know if you were there, but if you were, well, here were the projects. And here I have prepared my project. So I'll click on it. I've saved some designs. These are the two scenarios we were comparing. So I'll jump into the design interface of our software. So just a quick overlook on those who don't know RatedPower. We're a parametric software, so we'll have different tabs where we can set our different inputs, and then we'll run the design and automatically generate a layout. We'll do all the cabling down to the string cables, and then we'll generate a set of documents to back this layout and this design. So just to quickly explain what I've done here, this is my AC coupled BESS system. I have 9 megawatts AC. If you see here, I set a curtailment at the delivery point, so I could now size my BESS. So here I went and decided on AC BESS, decided on my power conversion system. If you're wondering how did I decide what size to install my BESS. So what I did with the documents we provide, I went here into the energy yield results, which will give me the energy yield for the whole lifetime of the project. And yeah, let me open this here. So we'll have a summary, we'll have the hourly production. In this case, I want to focus on the clipping and curtailment losses. Let me enable editing here. And so what I did, I just came here to filter, and I have the overpower loss of DC. So this would be the clipping of energy we did on the inverter if our DC to AC ratio was high. In this case, it's 1.2. So we'll have some losses, but it won't be a major thing. And since I have a curtailment at the delivery point, I'm more concerned on the AC losses. So what I did is just quickly sort this from largest to smaller and see that I'm almost losing a bunch of hours, 3 megawatts AC. So that's what I took into account to size my project. And then I also saw like how many hours a day are we having this curtailment, and then look for the optimal amount. In this case, I want to compare AC to DC with the same overall capacity. So here I went ahead and ran the design. And what do I get? So I get some financial output. And let me quickly explain to you, because we're seeing that we have an internal rate of return of 2.2. Is this low? Is this high? Well, it depends on the inputs we have used. So here on our financial tab, what we're using is a CapEx sheet where we get values from IRENA, the International Renewable Energy Agency, and from NREL for the best part. So for PV and the IRENA data, we have different CapEx sheets for different countries. So this will be automatically assigned depending on the location of our project. We're our international software, so we can run simulations anywhere, and will automatically adapt this CapEx sheet. So what we'll do here is we'll size this depending on the peak power, and for BESS we'll do the power install and the capacity. So these prices are orientative, but for this example, just I want you to take into account that we're just using these capex sheets, which may not represent the real market and different scenarios in different countries. So in order for you to get a more detailed financial analysis and more accurate financial analysis, what we can do is create our own capex sheet and at the prices we know we're working with in our market. So for example, for module, instead of having a unit for peak power, we can take the number of PV modules and then put the price unit here. So then the software will automatically get a total price of investment or for the capex based on the automatic POQ that we generate. So we can do the same for battery container. In this case, we're basing it on the capacity, but we can say here containers, so total number of battery containers, and then we'll go by price unit, and this will make our use case study more accurate. So I will close this. So what we'll do here is we'll iterate on these two base AC and DC, and we'll see how our financial KPIs change depending on different scenarios. So first one we did was AC and DC with a fixed price of, and we have here, we can set our revenue. As I mentioned, we have fixed price or variable price. And as you see, in this case, we'll have the AC being more profitable. We'll see here also how much energy we charge from the PV, the energy consumed from the grid. In this case, that is disabled, so that's will be 0. And then the average cycles per day. Why is this so low, like 0.32? Well, this is low because in my best dispatch, I set the cycles per day to 1. In this case, it went down to 0.5 because we're not reaching that clipping every day, right? So once I ran the design, this number adjusted to 0.5, but we're not reaching that clipping every day. So this is an average per the year. Okay, so what would happen now if we went and changed the financial revenue to a higher fixed price, right? This $40 per megawatt is maybe the average price in Spain. But what if we're in a different market that pays more on the megawatt hour? So we can change the price. As you see, as soon as I change something, the button of run design enables, and then we'll have our results quickly. I've also went ahead and already run this design just in case, we need to be prepared, but here we have it. So, well, is this one. If you see, we have 60. So what happens? The internal rate of return has gone up, right? Of course, if we're getting paid more for our energy, then it makes more sense to try to recover as much energy as possible and inject it to the grid. But of course, we're talking about arbitrage, right? So for arbitrage, we would never charge the battery if we could inject that to the grid, because if we had a fixed price, that wouldn't make sense, because we would be degrading the battery, but ending up getting the same price for that energy. So let's enable variable price, right? And we have here some prices for 2024 for the whole year. So let's see what happens when we run the design with variable prices. As you see now, what the software will do is take into account the production, the prices, and then optimize when it's better to directly inject to the grid or maybe charge those batteries to later discharge at a higher price. Sorry. So let's wait till we get those results into place. So yeah, this is exactly the same. So we see the IRR went down. So this way we can analyze different scenarios and see what would be best for our plant. And just reminding you, yeah, if we adapt those capex sheets to our market and our prices, the prices we have from our manufacturers and our subcontractors for all the installation and everything, to have a total price for the capex, then this will be more accurate. Perfect. So, and later what we'll do is we'll compare these different scenarios and see what's more profitable. So when is BESS more profitable? Well, when we're doing working with variable price, we need to take a look into how are those variable prices. In this case, we have a maximum of 193 and a minimum of -2 and a spread of 71. So what we need to keep an eye out for is the spread. So as the higher the spread, the more profitable it will be to keep that energy at the cheapest prices, and then uh, inject it to the grid when the prices are higher. So I want to make here another iteration where I have uploaded another prices, right, with a CSV file. I already have it here, and these prices have a higher spread. So we can maybe mimic some other markets. If we're going into Australia, which is one of like our most profitable markets, then we can generate this here. So let's see what happens and how our internal rate of return goes up. And as you see, we can quickly analyze different scenarios, play with our revenues, and see when it will be profitable to go ahead with this. So as you see, our internal rate of return went up a lot by creating this project in a market that will have a wider spread, right? So I've done here the same with AC, and it went up to 15.71. So now we can, once we do all our use cases and scenarios, we can save those designs. And let me go back to my folder. And what I'll do here is quickly compare them. I can do this by what I'm doing is here is changing the revenue, but I could be changing the capacity and anything I wanted, and then compare them. So here on the filters, since I'm focusing here on the internal rate of return, let me apply this, and then we can sort them. So here, of course, the lower, less profitable are the ones where we having a fixed energy price of 40. Then having a variable price with a small spread with DC won't be too profitable. Then we go with DC with a fixed price, a higher fixed price. Yeah, it increases, but still is not the best. The best. So here with AC variable prices, we go up to 5.53, and with a higher fixed AC, then it's good because we are trying to recover all that curtailment. And of course, what do we see here? That the most profitable is having a wide spread. So this means that we need to try to develop our best projects in markets that are that have a wide spread, so then we can get more profit on our projects. So we'll see how we can compare our different scenarios and take different inputs and make different designs and then compare them. And I think I'm running a bit out of time to go for the questions, but yeah, we have here our best energy results. We'll take a quick look on this. Whoops, not here. It's opening. So here we'll see when we store in BESS, when we charge from the PV, when we discharge, hourly for the whole year, right? And we'll see our energy flow. And here we have some tables, and we'll see when do we discharge. Well, here's where we're reaching our curtailment for the PV, but we discharge on these hours, trying to generate as much profit as possible. And then this will all be reflected also in the financial analysis, which will include all the revenue we're getting. Let me quickly show you. Yeah, so here we'll have the revenue for our BESS as well as the PV, and here we can jump into our hourly revenue, which will take into account the BESS price, the PV price, and what we're getting for the whole simulation of the project. Perfect. So let me go back to here. So just a quick conclusions on AC or DC. So first of all, is AC best for my projects, or is DC best for my projects? Well, it depends. It depends on all the inputs we have been seeing. That's why RatedPower can help us decide and evaluate different scenarios. Just a quick summary on sorry on our AC couple and DC couple BESS. For well, AC couple has the pros of AC couple. It has easy retrofitting. We can install it on already existing projects. It has greater flexibility. We can install it outside the PV array and the location. We can decide on the equipment, which is different from the PV, and it can support the grid services on the like a quicker response on the demand. But on the other hand, has more losses because we need to go from DC to AC, then back to DC to charge the battery, and back to AC to the grid. And also we need to invest in additional hardware, and we need to have their own inverter. And from on the other hand, DC couple BESS, we have a higher efficiency. We're charging directly from the DC side, so fewer losses, lower cost. We're already using the PV inverter we have for the plant, and then we can use that higher to DC AC ratio when we're reaching the clipping of the inverter. And then on the other hand, its flexibility is lower. We need to install it when we're building the new projects, and it needs the DC container needs DC BESS needs to be placed near the power station. And what we were mentioning before, if we have any fault in the system for DC coupled BESS, and inverter failure will mean the BESS is not working anymore because it needs to go through that inverter. So I think we're a bit over the time, but we still have some minutes for the questions. So if you want to drop them into the box, I'll make sure to answer them. And then if we don't get to answer all the questions, we'll make sure to answer them later if we don't get to answer them during the session. But thank you very much for your attention. Let me get to the questions. So here we have a question that says, can we enable charging from the grid to take that scenario into account? So yeah, we didn't get to do that here, but let's go with a which one? Yeah, this one we're using, the AC variable spread. We'll clone the design. We always clone the design so we can not edit any design and lose um, any design. So here in BESS, in the dispatch, now we're just charging from our PV field. So even if we're doing arbitrage, but we're doing arbitrage by not injecting the energy into the grid when the prices are lower and keeping it into the BESS. So we can enable charge from the grid and run the design. And what we'll do now is whenever we don't have it's not profitable to charge from the PV, or it would be more profitable to charge from the grid, then we'll do that analysis and take it into account in the best dispatch energy, in the financial revenues. So we take into account all the efficiencies. So now we're running like a big algorithm on the back end. Let's see if we get the results, and if not, I think maybe, yeah, here it is. So we can see how the internal rate of return has gone up. So this would be another scenario for us to compare. We see that we go for up by charging from the grid. Maybe if we bring our cycles per day to 2 and adjust that with our maybe yearly degradation, then we can study that. We can set here the maximum cycles per day, but the software then will optimize those cycles. Of course, if we're not charging from the grid and we're only charging from the PV, will never make sense to make more than one cycle per day. Perfect. Okay, so we got a question here, DC coupled BESS. How can we ensure compatibility of PV DC with BESS DC voltage and current, especially if PV part and BESS part from different suppliers? Well, in this case for DC, and yeah, you see how we change the rate of return. It went a bit down, so maybe it's not the best case to try to do more cycles. And sorry, I'm jumping back and forth, but yeah. So for DC, let me go back to DC. So we need to make sure for this compatibility. You're mentioning in the question that we are having the same voltage on the equipment. This we need to make see from the data sheet. For the moment here, when we're choosing our DC BESS, we're setting the power of our DC to DC converter, and we're not taking into account the the voltage and current. So this would be something we need to check on the data sheets of the manufacturers. So we have, can RatedPower do best technical design also like solar? Yes. So what we do, we were saying that we had the sizing tool and modeling tool. So what we have seen here is a bit on modeling tool on the arbitrage part, but we do also generate, and let me go to an AC, for example, here. We generate the best general layout, which we can download the PDF. Let me, the single line diagram. So since we're working a lot to improve BESS, and we'll be launching some different topologies and improvements to our documents, but let's take a look here. What we'll have is the BESS single line diagram to represent our project. I'm sorry. We'll have the layout, setting the containers. We can change the size of these containers. We'll have also the satellite image. here on the layout, we have by default set a 20 feet container for the PCS, 40-foot container for the batteries, but we can change these dimensions here and then change the distances from the blocks. How you account BESS degradation in the model is another question. So we do here in the dispatch, we do a yearly degradation that is taken into account in the model. We'll set the end of life state of health, and with this, we'll calculate the years the BESS project is operating, but this yearly degradation can be adapted to our specifications. If we bring the cycles per day, sorry, cycles per day up, then we can modify that yearly degradation. So this is how we account for the degradation in the model. So rated power only for energy arbitrage alone, or can the tool be used for other grid applications? So arbitrage is the first applications we have launched in rated power. We're actively working on developing further our best applications. So for the moment we have arbitrage, but we have had feedback of some frequency regulation inputs and so on. So you'll be seeing some improvements. But for the moment, the application we're modeling in rated power is arbitrage. Perfect. So I think we don't have any more questions. I thank you for attending this webinar, and we'll see you in the next one. And please make sure to reach out to us if you have any question, if you're watching this as the recording, and if you want to sign up for any other webinar, make sure to sign up. If the time doesn't work for you, we always send the recording after we have done the webinar. So I hope this was helpful and insightful, and feel free to reach out to me if you have any questions on how we model arbitrage in rated power or what we can do with BESS in rated power. Thank you very much, everyone, for joining. Appreciate your time.